I once drove a Jeep that had no brakes whatsoever. Whenever I had to stop for a light, my passenger would hop out and put a brick under the front tire. As a matter of fact, the only accessory that did work was the horn. If you have a vehicle with no brakes, I highly recommend that you have a functional horn. Now, sometimes it's inconvenient to have the passenger hop out all the time, and sometimes you haven't got a passenger. So, for those two reasons, vehicles are equipped with some sort of system to stop the vehicle conveniently from the driver's position. Now, it might take 50 horsepower for 5 seconds to accelerate your car to 50 kilometers per hour. By the Acme School rule number 12 of the universe, it will then take 50 horsepower for 5 seconds to bring it to a stop. Putting that in another fashion, to stop a moving vehicle, you have to get rid of its energy. The braking system of a vehicle is designed to rapidly convert that energy into heat. It does that conversion by a trick first discovered by the caveman: friction. Actually, friction comes into the picture in two different ways. The conversion of forward motion to heat is accomplished by contacting a rotating metal surface with a pad or shoe of softer composition. If the braking system is powerful enough to freeze or lock the rolling wheels, the tires will do that conversion of forward motion to heat. Friction surfaces are mounted on each one of the wheels. Now, to prevent you the necessity of jumping out of the car to activate them, there's a remote control system you can actuate with your foot. In the early days of brakes, the foot force was transmitted to the wheels by steel cables. Steel cables are fraught with problems, most noticeably rust and stretch. There is still a steel brake cable on your car. It's used to activate the parking brake. The serious job of daily braking is left to the science of hydraulics. Officially, hydraulics is the study of movement of water, but we're allowed to apply that name to other fluids as well. Hydraulics relies on two truths. A fluid is not compressible, and a pressure exerted on a fluid will cause the fluid to exert equal pressure in all directions. It's like some people I know. These cutaway models are hydraulic cylinders that are found on a car's braking system. The little one's from one of the wheels. When fluid's forced into it through this hole, the two pistons push out in equal distances with equal amounts of force. Now, some wheel cylinders only have one piston, but they're mounted so that the whole unit can slide freely. And by Newton's first law of brakes, this gives the same effect. The fluid's forced into the wheel cylinders by this one, found under the hood. There are actually two cylinders here with two pistons for safety. Each one operates half of the system. This little piston rod is pushed at both ends by the pressure in both circuits. If the pressure isn't identical, the rod will move a little bit, contact that wire, and light the brake warning light. These passages lead to a reservoir of extra fluid. In the event that the system loses any fluid, it's automatically added. And the brake pedal operates as a lever on this piston rod. Leverage can generate enough force to stop the car, but almost all cars now have an extra device mounted on the master cylinder, uses the powerful engine vacuum to move a diaphragm as you press the pedal. With this vacuum assist, your big toe can exert enough pressure to stop the vehicle. These are examples of what's found behind the wheels on a car or a small truck. The drum brake was the commonest type of brake assembly until the 1970s. Drum brakes all have two friction devices called shoes, but the shoes can have different functions depending on the layout. Larger vehicles use a layout like this called servo brakes. When the shoes are pushed outwards by the hydraulic cylinder to contact the drum, they attempt to rotate with it. Servo brakes have one large shoe and one small one. The way the shoes are anchored gives them a neat twist. When the small one contacts the drum, it's free to rotate a bit. This rotation pushes at the end of the bigger shoe, which can't rotate because the other end of it is anchored. The effect of all this is that the smaller shoe forces the larger shoe to press harder on the drum, aiding the friction. Servo brakes work when the vehicle's reversing, but then the larger shoe is forcing the smaller shoe into the drum. Brakes on smaller cars use two equal-sized shoes that are self-pushing. You can get an idea of how a shoe wedges itself into the drum by moving one hand over the other like this. In this type of brake, only one shoe really does the braking, depending on which way the drum's turning. The extra parts here are to adjust the position of the shoes as the friction surface wears, and to allow connection to a steel cable that can lock the brakes on for parking. there's a good chance that drum brakes still exist only because of the ease of making that parking brake linkage work, because there's a much better brake assembly. If you ever noticed the way the front of a car dips when the brakes are applied, you already know something important about the car's braking system. The front brakes do most of the work. The self-wedging action of the drum brake is good, but it means the shoes need spring action to return them to rest, and because of that, they need some means of adjustment as the shoes wear down. Also on their bad side, the outward push on the drum, coupled with the heat generated, can distort the shape of the drum, and the drum collects dust and grit of all kinds. This is a disc brake. It works like this. The disc is exposed to the air, and that helps keep it clean and dissipate heat. As well, friction pads push equally on both sides of the rotating surface, so there's less chance for distortion. The unit that pushes the pads contains a hydraulic cylinder that pushes only on one of the pads, but the whole works is free to slide a bit, so an equal force gets centered on that rotor. Now, since there's no self-wedging action, no springs are required. When there's no pressure on the hydraulic piston, the pads ride right alongside the rotor. As the pads wear, more hydraulic fluid fills up behind the piston to take up the slack. In a car with disc brakes, you'll notice fluid slowly disappearing from the fluid reservoir as the pads wear. Here's a disc pad. This little tab has an interesting function. When the pads get thin enough to require replacement, it contacts the rotor and makes a screeching noise. In any event, if you hear any odd noises from the braking system, it's probably time to have it checked. Either that or make sure you always have a passenger with a brick.